All right, everyone, let's get started. Today, we're going to talk about something that happens way, way before a single line of code ever gets written. It's like the invisible scaffolding of every great application you've ever used. It's the blueprint that separates really elegant, robust software from, well, from a tangled mess that nobody wants to touch. We are talking about software design. And let me tell you, this is the art and science of planning, and it's probably the most important skill you're going to develop as an engineer. So let's dive in.
So here's our roadmap for today. First, we'll start with the why design is so critical. Then we'll get into the core principles, the stuff that makes for a solid foundation. After that, we'll tackle a huge challenge, managing complexity, before we look at the different ways you can actually approach design. Then we'll check out some specific methodologies. And finally, we'll wrap it all up with the key things you need to remember to build better software. Sound good?
Okay, let's jump right in with Section 1, the blueprint for code. Look, I get it. The temptation is to just start coding, right? To get your hands dirty and make something happen. But before we even think about the what or the how, we've got to spend some real time on the why. Why do we bother with all this planning? Because honestly, understanding this is the absolute foundation for everything that comes next.
So what do we even mean when we say software design? This definition here is actually a really great starting point. It's a process of defining the architecture, components, and interfaces. Let's break that down. Architecture is the big picture structure. Components are the individual pieces of the puzzle. And interfaces, those are the rules for how all those pieces talk to each other. So imagine we're building a new social media app. The design phase is where we'd ask, are we going to use a microservices architecture? What are the key components going to be? A user profile service, a newsfeed service, maybe a messaging service? And how will they communicate? Through APIs? These are the huge questions we answer before we write a single line of code.
But it's a fair question, right? Why spend all this time drawing boxes and arrows when you could just be coding? Why is this abstract planning process the absolute key to making a system that actually works and, lasts? And this slide, this really gets to the heart of it. Just imagine hiring a construction crew, pointing to a giant pile of wood and nails, and just saying, build me a house. I mean, it would be a total disaster, right? You'd have doors that open into walls, stairs that go nowhere. It'd be complete chaos. A blueprint is what prevents that. It makes sure the foundation is solid, the wiring is safe, and that everything actually fits together. That is exactly what software design does for our code. It's the plan that turns a pile of programming statements into a functional, reliable system.
And the payoff for all this planning? Oh, it's huge. First off, maintenance. A well-designed system is a dream to update. A poorly designed one? It's an absolute nightmare. Second, all those things we care about, reliability, performance, security, those don't just happen by magic. They are baked into the system at the design stage. Third, it actually makes teamwork possible. A good design is like a shared map for the entire development team. And finally, reusability. Why reinvent the wheel every single time? A good design lets you build components you can use over and over again, saving you just a ton of time down the road. Okay, so now that we know why design is so important, let's talk about the what. What are we actually trying to do? Well, these are the core principles, the intellectual tools that every software engineer uses to create quality, maintainable systems. First up, abstraction. This one is a cornerstone of good design. It's all about hiding complexity. The car analogy is just perfect for this. When you get in a car, you press the gas pedal, and the car goes forward. You don't need to know about the engine or the fuel injectors or the transmission. All that complex stuff is hidden from you. You just have a simple interface, the pedal. In our code, this means we create functions or classes that have a simple, clear purpose without exposing all the messy details of how they actually get the job done. This makes our code so much easier to use and to understand. And this quote just nails it. Abstraction lets us focus our brainpower on the big picture. By hiding all those nitty-gritty low-level details, we can think about the system at a higher level and solve the really tough architectural problems first. Next up, we've got modularity. This is basically the divide and conquer strategy of software design. You take a huge, complex system and you break it down into smaller, manageable, and this is key, independent pieces called modules. It's like building with Lego bricks. Each brick has a specific purpose, and you can work on one or even replace it without messing up all the other bricks it's connected to. This makes developing, testing, and maintaining everything so much easier.
And that brings us perfectly to our next point, information hiding, or as you'll often hear it called, encapsulation. These two ideas, modularity and encapsulation, are really two sides of the same coin. Modularity is about breaking things into pieces. Encapsulation is about making sure those pieces don't mess with each other's internal business. See, each module has a public interface. It's like a contract that says, this is how you can talk to me. Everything else, it's private. This is incredibly powerful. It means you can completely change how a module works on the inside, maybe make it way more efficient, and as long as you don't break that public contract, the rest of the system won't even notice. Now, that idea of modules being independent is so critical that we're going to dedicate a whole section to it. So let's talk about managing complexity by taking a deep dive into a concept called coupling. This is basically a measure of just how tangled up or how interdependent your different modules are.
Let me be absolutely crystal clear about this. If you only take one thing away from our talk today, let it be this. Your goal, always, every time, is loose coupling. This means your modules are like polite strangers. They interact through very well-defined channels, but they don't know or care about each other's internal drama. This independence it's the holy grail of software design. It's what lets us build systems that can grow and change over time without completely falling apart. So this slide here shows the two extremes. On the left, you've got loose coupling. Think of a simple function that just takes a number and returns its square. It doesn't care where that number came from, and it doesn't care what you do with the result. It's totally independent. On the right, though, you have tight coupling. Imagine a module that, to do its job, directly reaches into another module and grabs the value of a variable. Yikes. Now, what happens if the owner of that variable decides to change its name or its type? The other module instantly breaks. This creates a really fragile, tangled mess, where one tiny change can cause a domino effect of bugs across the entire system. And that is exactly what we want to avoid. Now, coupling isn't just an on or off thing. It's a whole spectrum. And look, you do not need to memorize all these terms, but it's really important to understand the concept. On the good side, the best side, you have data coupling. This is where modules just pass simple data back and forth as parameters. It's clean, it's explicit. On the absolute worst side, you have content coupling. This is where one module literally reaches into another module and messes with its internal state. That is a massive violation of encapsulation, and it's a recipe for disaster. Our goal is to always live on the best side of this spectrum, where our modules are talking to each other in a clear, controlled, and predictable way.
Okay, so we've covered the core principles. We know what we're aiming for: modular, loosely coupled systems. But how do we actually get there? What's our strategy for attacking the problem? Well, that brings us to our next section, where we'll look at two fundamental approaches to the design process: top-down and bottom-up. Top-down design is pretty much exactly what it sounds like. You start with the entire system as one big idea, and then you systematically break it down into smaller and smaller subsystems and components. You go from the general to the specific. This is perfect when you're designing a brand new system from the ground up. Now, bottom-up is the total opposite. You start with existing low-level components, maybe from a library you already have, and you build them up into larger and larger systems. This approach is fantastic when you want to create a new system by reusing a bunch of existing parts.
All right, so we have our strategies, top-down and bottom-up. Now, let's go one level deeper and talk about design methodologies. These are more than just processes. They're fundamental philosophies about how to think about and structure our software. This is about the lens through which you view the entire problem you're trying to solve. And this table gives us a fantastic side-by-side comparison. On one side, we've got function-oriented design, or FOD. This approach focuses on the verbs, the actions. You think about the system in terms of what it does, and you build functions to make those things happen. It's often associated with the classic software development lifecycle. On the other side, we have object-oriented design, or OOD. This focuses on the nouns, the things. You model your system around real-world objects, like a student or a course. And each object holds its own data and behavior. As you can see in the table, OOD generally leads to systems that are less risky and way more reusable because that data is protected inside the objects. But hey, FOD can still be a really simple and effective approach for smaller, more procedural kinds of tasks.
All right, we have covered a lot of ground today. We've gone from the fundamental why of design all the way to principles and methodologies. So let's bring it all home and just summarize the most important points from this entire explainer. These are your key takeaways. So let's pack our design toolkit. First and most important, the blueprint. Never, ever start building without a plan. Second, your 3 essential tools: abstraction to hide complexity, modularity to break things down, and encapsulation to keep them separate and safe. Third, your guiding principle, your North Star. Always, always, always aim for loose coupling. Fourth, your 2 main strategies: Top down for new projects and bottom up for reusing existing parts. And finally, your two main philosophies, function-oriented and object-oriented. Knowing which one fits the problem is absolutely key. And that, everyone, is the foundation of software design. See, it's not really about writing code. It's about thinking. It's that disciplined, creative process that lets us build software that's not just functional, but also elegant, maintainable, and scalable. You now have the blueprint. You've got the tools. The question isn't just what you'll build, but how you'll build it. So go out there, design thoughtfully, and build some amazing things. Keep exploring, keep learning, and thanks for watching.